Hi everyone, this lesson is about using Simpsons rule. So this is the last of our numerical integration formulas, and you can see we have Simpsons rule written out here. It's written out in full there. The second line is the way that I like to use Simpsons rule. So this one here is the way I like to use this. I'm not so fond of this last one because although the evens and the odds are clear, sometimes people forget that the x means the first and the last one. But look, you can use either one. As we've seen before, the lower limit, which we call a, this is referred to as x naught in our rule. The upper limit, which is also referred to as b, this is referred to as xn. Now in our case, n equals 10, so I'll write x10. As with all of the other rules, we would first start by looking at things like, well, what is the width of our little partitions here? So it's the upper limit, subtract the lower limit, divided by n, and in our case we have 6, take 1 over 10, or the width of each of these is 0.5. Now w appears at the start of Simpsons rule here, so it's important to calculate w like that. Our function that we're dealing with in this case is 1 over x. But of course, as I've said before, it can be any function whatsoever. I'm using this just to illustrate the same function with different techniques. Now, 1.5 here, this is x1. 2, that's x2. This one's x3. This one's x4, and so on. Now it's probably important to label a couple here at this end as well. That one's x9 and that one's x8. Because the distinction here, of course, is that we have to sum the values of the function where x1, x3, x5, the odd ones in other words. So that one, all the way up to that one will have to be summed. And then separately in this calculation, we have to use x2, x4 and so forth. So that's x2, x4, the ones in between up to x8. Now the even ones do not include the terminals at either end. The terminals are taken care of here and here separately. So Simpsons rule is more complicated. Let me just highlight these odd ones in yellow and the even ones in green. As I said, Simpsons rule is more complicated, but the price of that extra complexity is we get a much more accurate estimate. Because for those who've watched the previous video, we're no longer using straight lines. We're using a parabola to emulate our function from here to here to here. So 3 points are enough to define a parabola, and if we had a parabola running along those 3 points there, that would be a very close approximation to our curve, and then we calculate the area under both of those strips by integrating the formula for the parabola. Then we do the same thing for the next 3 points, different parabola, and likewise with those ones, and then those two there, and then those two there. This is why Simpsons rule has to have an even number of partitions, because we work in groups of 2. Now let's see how we actually apply the formula in our calculator. So we have integral from 1 to 6 of our function 1 over x dx, and we'll say this is approximately equal to, let's just write the rule, w over 3 f of x naught plus 4 times the sum. So like I said, that's sum there, and I'll write f of x odd plus 2 times the sum f of x even plus f of x. Now this would normally be written as xn. In our case it's x10 because that's our last one, but of course we don't have to use 10 partitions. We could use more if we chose. Now before we get too far, W, we have a substitute for that. X0 is 1, Xn is 6, that's all good. But these odds and evens require a little bit more thought. So let's think about what X odd really means. The odd ones, they start at 1.5, then they jump to 2.5, then 3.5, then 4.5, then 5.5. Now that sequence of numbers there seems like an arithmetic progression. It seems like an arithmetic progression that starts at 1.5, and we have an increment of a common difference of 1, which we would need to multiply by some counting variable I. What would be the limits on I? Well, if I was 0, then that would turn out to be 1.5, which is what we need. This is my dummy variable I that I'm using to count. And if I wanted to finish at 5.5, the last of the odd ones, then I'd need I to equal 4. So that's going to be a handy little thing to use when I'm writing in X odd into my calculator. I'd better think about X even as well. So the even ones here I've highlighted in green, they start at 2, then to 3, then to 4, then to 5. So that also is an arithmetic progression, starting at 2, common difference of 1. Now I'd better use a different counting variable this time, so I'll use J. And what would be the lower and upper amounts that I want for J? Well, I wanted my value, my lower one for the evens to be 2. So if J was 0, that would calculate out to be 2. And I wanted the largest one there to be 5. So if J were 3, that would count out to equal 5. Now you notice that I and J counting variables, different increments. And that's where I'm going to, and once again I've written these in the way of what I was trying to do, so I'll just move those slightly down to there, perhaps over to there. Let's do that. Now it's time to get my calculator out and see if we can actually get the calculator to perform this for us. So what have we got there? Let's just delete that last one. Actually, why don't we delete all of them? There you go. Now remember, we need to first of all set up our function 1 over x in our graphing app. There it is from last time, so 1 over x, and I can refer to my function where I have f in the formula, I can refer to it as y1 on the calculator. So let's pop back to our calculation screen. Now let's begin. W was 0.5 over 3. Open a set of brackets. Now I need f of x0. Remember, I need to hit the variables key, the graphing submenu, and then F1 for a y variable. It's the first of my y variables, and I'm substituting x0. I know the value of that one is 1 from my diagram. Plus 4 times the sum. So I'd better go, hit the wrong key there. Go back into that one. Just hit the exit key to get back to here. I need the maths options, across to the right, and sigma notation is here. Now what do I need the sum of? I need the sum of f, and that is y1. So, graphing y1, a little pair of brackets there, and in the green brackets is where I'm going to be writing x odd. Now this is what I wrote down here, 1.5 plus I. Alpha I. And what were my limits here? Well, the counter I had to run from 0, start at 0 and run to 4. So 0 there to 4. Plus 2 times, now this is where I'm up to the sum of f of the x evens. So back to the maths menu, sigma. Now I need my y variable, little pair of green brackets, and the inside there is where I write x evens. Now, how did I think x even would go? It would be 2 plus j. 2 plus, and j is there, and my variable, my counting variable j, went from 0 to 3. Now I'm at the end there, I just have to add in plus f of x n. So that would be my, oh, it was already there. My mistake, it would be my y variable. Whoopsie, forgot to add the plus sign. Here's a bracket, and it is, oh, making lots of mistakes. It's y1. Now, what was my final x value? It was 6. Close that bracket, close out the big brackets, hit enter, and there's my result, 1.793, which is very close to the true answer. Let's just write that down. My result then, 1.793, and the next decimal would have been a 2. If we take a little look back up at the diagram there, you might just be able to make out that the true value of the integral is 1.7918. So by far, Simpsons rule has given us the best estimate to date of the different techniques we've done. Now, I don't know of any common technique which is better than Simpsons rule. So that's the end of the little numerical integration series. We've done midpoint rule, we've done trapezium rule, and now we've done Simpsons rule. And yes, it's more complicated. For one like this, where there wasn't actually that many, you might not have worried about all of the fancy stuff on the calculator. Why did I teach you all this stuff on the calculator? So that when you use more than 10 partitions, you can calculate it out, because it's really just a matter of changing these numbers and the width of the partition and so forth. And the formula gets no worse than what it looks there. That's as bad as it gets. Just extra variables, extra counters. Counters go to higher numbers, increments are smaller. That's the sort of thing that happens. So that's it for this time, and hope you've enjoyed that, and I'll see you next time.